Hello everyone, this is Anand Ranjan. On behalf of School of Computer Application, Narsidas University, I welcome you all in the video lecture series of Digital Electronics. And in this video, we are going to discuss about the decoder circuits. Alright, so decoder are another category of the combinational circuit, and in this decoder circuit, just we have written over here, the decoder is a combinational circuit that converts the binary coded data into the other format. Like if you have a binary number, that can be converted into either octal, decimal, or other hexadecimal number. So these circuits are used to convert one form of information into the another form, and a binary coded of n bit can represent 2 raised to the power n distinct elements, as we know, because n variables can represent total 2 raised to the power n different combinations. So we can say a binary coded of n bit can represent 2 raised to the power n distinct element. A decoder has an input and less than or equal to 2 raised to the power n output. This is the conceptual block diagram of a n cross 2 raised to the power n decoder, in which you can see that on the input side we have n number of input and 2 raised to the power n outputs. So as far as the size of the decoder is concerned, we also called it as n cross 2 raised to the power n decoder, n lines to 2 raised to the power n line decoder, or 1 is to 2 raised to the power n decoder. And why we do say this 1 is to 2 n decoder? Because at a time only one input is to be applied, and out of 2 raised to the power n output, one output will be selected. So we can say this 1 is to 2 raised to the power n decoder circuit. There are certain examples of the decoder circuits. These are 3 is to 8 decoder circuit, 4 is to 10 decoder circuits, or 4 is to 16 decoder circuit. So we'll start with the first fundamental or the basic 2 is to 4 decoder in the next slide. So but before that, let's try to understand the concept of enable also, because in every combinational circuit we have the concept of enabling and disabling, and by this input we actually translate our input to the outputs, and we can stop transforming inputs to the output by disable it. So we have two types of enable inputs. In one is the active high enable input, and another is the active low enable input. In short, the active high enable input is known, also abbreviated as AHE, where if you put E is equal to 1, then the circuit will be enabled with the active high input, and you can the input will be translated to the output. While if E is equal to 0, then it will be enable input will be inactive. There will be no transformation of input to the output in the combinational circuits. Then the active low enable input, just this is the opposite of what we have seen in case of active high enable input. Means if E is equal to 0, then the active high input means your input will be translated to the output. But in case of E is equal to 1, the there is an inactive, though no transformation from input side to the output side will take place. Okay, so there is an important note point regarding this enable input, is that the enable input is an output input that provides the flexibility to activate and deactivate the circuit as per the system requirement. So somehow it is actually a control input, you can say, and by externally you can easily operate or you can easily control the circuit by switching on and off of the these kind of devices. So let's start discussing the 2 cross 4 decoder circuit. This is the fundamental or the basic decoder circuits we are having. in which the enable input is mentioned over here with the two input X and Y and the four distinct output D0, D1, D2 and D3. So as we know, with the two inputs we can generate four different combinations. So these are four different combinations, 0 0 0 1 1 0 and 1 1 written over here. And if enable input, we are considering the case of active high enable. So if E is equal to 0, then no matter what input you applied, your output will always have 0. This row is actually specifying this concept. Okay, and when this enable input is 1, then your circuit will be operational, and for every input combination there is a distinct output. For example, if you have a X0 and Y0, then D0 is 1 and the remaining all are 0. Similarly, for 0 1, the D1 output is there and remaining all are 0. And if 1 0 input the combination you choose, then you will have output D2 and the remaining all three are 0. And for 1 1, the outputs 3 output 0 and only D3 in outputs are actually chosen or selected. So these four distinct output can be written in terms of the min term, or in terms of a Boolean expression we can say. So D0 can be represented as E X bar Y bar, D1 can be represented as E X bar Y, D2 can be represented as E X Y bar, and D3 can be represented as E X and Y. So these all four expression can be easily incorporated, easily implemented using a simple Boolean means simple logic gates. So this is the implementation diagram where the enable input is represented by the green line, and we put it on 1 just to represent that the circuit is in enable state, and these X and Y lines along with their complements are here to select the specific product term like this one. So for example, for D0 we have E X bar Y bar. So if we choose this E line over from the this line, and then we choose X bar from the complemented of X bar line and Y bar from the complemented of Y bar line, and pass it into a AND gate to get a product term E X bar Y bar, which is nothing but D0. And similarly we incorporate D1, D2 and D3. So this is the simple 2x4 decoder circuit with active high enable. Important note point, let's take here that in a decoder at any instant only one output is at logic 1 and all other output is at logic 0. So this is a kind of 1:1 you can say input and output behavior we can exhibit in case of the decoder circuit. Now let's try to implement the Boolean function using the decoder, because these decoder ICs are very much popular to implement the some basic or the elementary combinational circuits. So we can able to implement those with the help of decoder circuit. And n cross 2 raised to the power n decoder generates all 2 raised to the power n possible minterms for the n input variables, and any Boolean functions can be implemented in the sum of minterm form. Hence we can say the function can be implemented by summing or ORing the desired minterms which these decoder ICs are producing. So let's take an example of implementing a multiple output function using a 74LS138 decoder IC, and the external with also external gates. So for example, these two functions are given to you, F1 and F2, which you need to be incorporate, which you need to be implement using the decoder IC. So this is the conceptual block diagram in which the three inputs A, B, C are there. And because as you know, the 3:8 decoder 3 inputs will be there, and the 2 raised to the power 3, that is 8 outputs are there. And just because this ICs come with the active low enable input, so we mark the bubble at the output like this. So it simply generate all the 8 different combinations for the ABC different variables, and we have to just choose smartly only those functions and pass to the NAND gate. For example, function F1, we have to choose 1, that is this 1, then 4, then 5 and 7, and pass it to a NAND gate. And for example, this IC, if in general we are not talking about a specific 74LS138 IC, and we do not compulse or we not put any condition like bubbling over here, then you have to choose these output lines and just pass to a OR gate. But just because of the nature of this IC, the active low enabling, we have to choose this NAND gate. And similarly, for the POS or the expression implementation, here means pi M2367, we have to choose these lines 2, 3, 6, 7 from the output line and pass to an AND gate, so that we will implement the F2 function in this. So this is a simple conceptual diagram of the application of the decoder to implement the Boolean function or to implement the Boolean expressions. Next, let's take another example in which we actually implement the full subtractor using a decoder or write the truth table. So this is another example. So first of all, we'll write the truth table for the full subtractor circuit, and then we will write the Boolean expression for that, and with some inputs and output behavior, we choose decoder IC to implement it. Okay, so for example, let's first write the full subtractor circuit. So this is the truth table for full subtractor, in which the inputs are AB and borrow in, and the outputs are difference and borrow out. Keeping into consideration the minterm representation, we write these expression D and B out by considering the minterm approach. So this is summation M 1, 2, 4 and 7 for the D difference, and for the borrow out we choose summation M 1, 2, 3 and 7. Okay, so these two expression actually completely completely represents the full subtractor circuits, and with the help of these expression we will construct, or we will and with the decoder IC we will implement our full subtractor circuit. So again we are taking the 74LS138 IC, which is the 3:8 decoder with active low 2 active low enable input. So these are the three inputs A, B, C, and these are our 8 outputs starting from Y0 to Y7. We have the Boolean expression for difference and B out like this, and at this time we have because both SOP expressions are given to us, so we simply choose NAND gate to accommodate all the minterms associated with the D and B out. So for difference we choose 1, 2, 4, 7. So this is 1, 2, 4 and 7, and pass through a NAND gate. Similarly, another NAND gate we take to produce the B out, and for that we choose 1, 2, 3 and 7. 1, 2, 3 and 7. Okay. So in this manner we can able to implement our full subtractor circuit using 3:8 decoder IC. Now, just in the previous lecture, we also have discussed the 2-bit magnitude comparator, and that 2-bit magnitude comparator can also be implemented using the decoder IC. But for implement that, we have to choose 4:16 decoder, because in the 2-bit magnitude comparator, we have taken B0, B1, A0, A1 as the 4 input variables, and these are the output Boolean expressions are written for the A greater than B, A is equal to B and A less than B. So this is the implementation of the 2-bit magnitude comparator using a 4:16 decoder IC. Here you can see these are the input lines, and in general we are considering here the active high enable, so that this E is equal to 1 we have. So with the 4 inputs, these are all 16 possible minterms for we are written over here, starting from D0 to D15, and for implementing A greater than B, the minterm M4, 4, 8, 9, 13 and 14, we choose those from these output lines and pass through a OR gate, so that we will get a function for A is greater than B. For A is equal to B function, the minterms are 0, 5, 10 and 15. So here we choose these D0 line and D5 line, D10 line and D15 line and pass through an OR gate. So we'll have A is equal to B implementation, and for A less than B Boolean function implementation, we have to choose the lines 1, 2, 3, 6, 7 and 11. So this is the overall implementation of 2-bit magnitude comparator using a 4:16 decoder IC. Now in decoder we have one more type of problem is there, which says means designing a greater size decoder using with the help of small size decoder. Okay, so in this slide we actually try to understand means how to implement a large size decoder with the help of small size. Okay, so a small size decoder with enable inputs can be interconnected to obtain the larger decoder size. So first we try to understand means how to make a 4x16 decoder using 2:4 decoder. So in this diagram you can see we first construct a 2:4 decoder with the input W and X, and with which can be produced W bar, X bar, W bar X, WX bar and WX, and they actually enable the next layer of 4 decoder 2:4 decoder sections, by which actually a specific IC will be selected or a specific decoder will be selected, so that the inputs to that concern will be passed to the output, which constitute D0, D1, D2, D3, and similarly at the output of all 4 decoder in that line can be nomenclated starting from D0 to D15. Okay, there is another way you can understand this concept like this. At the first layer you actually choose W bar, X bar, W bar X, WX, and at the second layer you have to choose from Y and Z in this manner. So you will have all the possible 16 output lines starting from D0 to D15. So in this case the smaller size decoders can be used to implement the larger size decoder. Next, this is an example of how to construct a 4:16 decoder using 3:8 decoder, in which we actually take 3 inputs X, Y, Z, and W we actually choose smartly with the help of one inverter, and this W input is given to the both enabled input to the both 3:8 decoder, so that if you look at this table, then initial 8 are actually constitute the W bar and the remaining 8 are W. So at a specific for the 8 min terms only one IC will operate, and for the remaining will be in off situation, and while the second will be in on, the first will be in on off situation. So in this case also we can generate all 4 inputs, means including this W, X, Y and Z, all 8 outputs, D0, D7 in this first one, D8, D15 in the second one. Okay, so this is the implementation of 4:16 decoder using 3:8 decoder IC. Okay, thank you so much. We will continue our discussion on the different combinational circuit in the coming lecture. Thank you so much. Thank you.